Mantas Garnevičius. Mantas, are you ready? Yeah.
Yes, I'm ready.
Here. Perfect. Then the floor is yours.
Okay.
For 20 minutes.
So, hello. My name is Mantas Garnevičius. I'm a PhD student in Vilnius Gediminas Technical University. I will talk about my paper on the topic of experimental and numerical investigation of bond behavior of synthetic macro-fiber in concrete. Fiber nowadays is used in various fields. It's used for bridge decks, runways, tunnels, and concrete floors. It is used to prevent brittle fracture of the concrete and to increase crack resistance. The significance of the fiber adhesion property study modeling example. So the interaction mechanism of synthetic macro-fibres and concrete is the object of this research. This mechanism is responsible for the residual strength of the fiber-reinforced concrete, the essential property describing the efficiency of fibers. The bond strength and the corresponding deformation modulus define the interaction mechanism. There is no universal methodology developed for evaluating these parameters. The adequacy of the determination of the bond properties is essential for the development of a mesoscale numerical model of fiber-reinforced concrete. And this is an example of such a model. So by determining the arrangement of fiber in concrete, observing existing structures, defects, and cracking, we can use that knowledge to develop a more detailed numerical model that will allow a more accurate assessment of the influence of fibers and allows development of new research methods. In order to create a more detailed numerical model, it is necessary to determine the adhesion properties of fiber and its distribution and orientation in concrete. Synthetic macro-fiber pull-out test. So the aim of this study is to experimentally determine the parameters of adhesion between the selected synthetic fibers and concrete and to create a numerical fiber pull-out model. The object of research is the adhesion of synthetic macro-fiber with concrete, performing one fiber pull-out tests. We use two different types of fiber. One is Durus S400, the other one is Durus Easy Finish. Both of these fibers were selected because they were widespread in the market and they were 4 centimeters of length. We determined that the most effective embedment length in concrete of fiber is 20 millimeters. So when a crack forms in the middle of this kind of fiber, it would be embedded in concrete at about 20 millimeters on both sides of the crack. So fiber adhesion to concrete properties determination test. So we prepared the formwork in the innovative structures and material laboratory at my university. Then we used foam squares to divide the forms into the lengths for the cubes, concrete cubes. Then we placed the fibers in the foam squares to fix them in position. After that, we mixed the concrete, performed a concrete slip test, and poured the concrete into the forms very carefully, not to damage or move the fibers already placed. After the concrete was poured in, we put in another fiber on the top of it. Then to condense the specimens, we vibrated the stall. And after that, we left it to harden for 30 days. Determination of the bond property. So when the cubes had hardened, we used a plastic sleeve to protect the fiber itself from damage because we used steel clamps to fasten it into the apparatus, which then measured the displacement and the pull-out force during the tests. This was pretty hard to do before we started using the plastic sleeve because it would damage the fiber itself, and then the test would just be useless because the fiber would show a completely different kind of strength and it would break very often. There were 3 outcomes of these tests. One, the nominal outcome of the test was the fiber to be pulled out of the concrete. Then the other 2 uneven outcomes were when the fiber would fail, it would just break from the force, from the load. Then the other uneven outcome when the fiber would be damaged during fastening, and it would also break, or it would be it would have a very weak bond with the concrete. That was most cases with the fiber that was put on the top of the cube. After all of the tests were completed, we created load displacement diagrams for both of the fiber lengths and the fiber types. As I've said before, the load and displacement diagrams were also created for fibers embedded at the top of the concrete cubes. It had been experimentally found that the extraction forces and displacements of these fibers at the top of the concrete cubes are more scattered. The tensile strength decreased on average by 20%. The scattering of the results increased to 70% compared to the fibers embedded in the lateral planes. The graphs are given below. The top one is the top plane fibers, and the lower one is the lateral plane fibers. Numerical simulation of fiber pullout test. The purpose of modeling is to create a numerical model of fiber and concrete according to the mechanical properties of 10mm embedded fiber and the determined strength of concrete with the finite element program Athena. Select the model adhesion parameters so that the modeled fiber displacement corresponds to the load and displacement diagram of the experiment. The obtained material and adhesion parameters in the development of a numerical model of 10mm embedded fiber extraction are applied to the development of a numerical model of 20mm embedded fiber extraction. The software we used was Chervenka's Consulting Athena. It was used because it allows the creation of your own material models. It has a nonlinear concrete model already developed, and it allows to adjust the object adhesion parameters. So first in Athena, we created the geometry of the cube and fiber. The fiber geometry is described by a fictitious fiber diameter and fiber length. Since the cross-section of the fiber is not circular, the size of the equivalent rectangle must be calculated from the given fiber diameter. This is done by using the following formulas given below. Once the geometry of the model was created, it needed to be divided into finite elements. The number of elements used is very important in the study because if the results of the calculation depends from it. If the model is divided into too few finite elements, we will get huge errors, and if into too many, the calculation will take too long. Therefore, it is necessary to find the optimal number of them. For this purpose, several different models with different numbers of finite elements were developed, and the results of their calculations were compared with each other. After comparison between the models, it was found that we can just more densely divide the area around the fiber itself, and the concrete cube part in which the fiber was embedded, and dividing all of the rest of the cube into bigger finite elements. And when we compared the results of such a divided cube with the other cube that was divided very densely whole, it was found that the accuracy of the calculation was very similar. And by doing this, we reduced the amount of finite elements needed from 67,000 to 3,700, and the computation time was reduced from 12 hours to about an hour and a half, 2 hours. The modeling process. The fiber is modeled as an isotropic elastic material according to the material parameters specified by the manufacturer. The concrete was modeled using a physical nonlinear material model developed by Chervenka Consulting. The calculation results are determined by the described parameters of concrete and fiber adhesion. These Parameters are normal stiffness, tangential stiffness, tensile strength, cohesion, friction coefficient, and a fiber slip graph. We repeated these simulations for dozens of times to obtain the graph, to obtain a graph that would be consistent with that which was obtained in the laboratory during the experimental tests. After we using this approximation method, the adhesion parameters were finally determined, with which the model and experimental results correspond with only a 3% error. These tests took a long time, about 2 months, leaving about 10 calculations a day. And the determined adhesion parameters are given below. The 1 centimeter and 2 centimeter calculation results. When we calculated and managed to replicate the test for the 1 centimeter embedded fiber, we had to apply those parameters to the 2 centimeters embedded fibers, and here we managed to do it. The shear stress visualization is given here at different points during the pull-out tests, the stresses in the concrete cube and fiber. So the aim of the work was achieved. After the experimental research, the parameters of adhesion of synthetic fibers to concrete were determined, and a universal suitable for calculating different embedment lengths extraction model of synthetic macro-fibres was developed for the analyzed fiber. After the experimental test, the extraction forces and displacement diagrams of the synthetic macro-fiber were determined, according to which the 10 millimeter embedded fiber diagram was selected for the adhesion to concrete modeling. The model developed for 10 millimeter embedded fiber is adapted to a model to model the extraction of a 20 millimeter embedded fiber. The obtained modeling results are compared with experimental measurements. The error found does not exceed 4% on average, and we compare the deformation energy, that is the area beneath the graph. So thank you for your attention.
Thank you for this nice presentation on time. You respect exactly the time. Now we go for some question. I think Balas have some question. If I saw that.
Yes, thank you. I can start, of course. Congratulate to your presentation and to your work, very interesting. And we need more research with polymeric fibers. My first question concerns the shape of pull-out force displacement diagram. What is your explanation that all the diagrams are very undulated? This is the part of the phenomenon, of course. There is a special slipping, or how does it create this undulation? Why?
You mean the different diagrams, they differ a lot.
The diagrams go up and down, up and down.
Yeah. So first it's because of concrete, because it's such a material. Second, I think these are so different because it was the first test we ever completed, my first tests I've ever done. So there were some mistakes, probably.
Not necessarily. Not necessarily mistake.
No, I mean that we might have. Well, you see, it's a very. The mechanism of how we fasten these things, it's very easy to damage the fiber itself. So if you would fasten it a little bit too hard or a little bit too easy, it would either slip out of the apparatus or it would get damaged a bit, and then these diagrams would differ. We threw a lot of these diagrams out because we had 8 specimens, so about 16 fibers for every embedment length and type. So we threw a lot of them out, and when they did the modeling part, they used only the results of those who they knew that were done correctly. Well, there wasn't any questions about them.
Okay. in the paper, I read also the paper, of course, you are speaking at the beginning a lot about top bar effect. So what is your evaluation for the top bar effect? All of your fibers were inserted in the top of the specimen.
Those fibers that were inserted in the top of the specimen, well, I think they either sunk down or they were pushed out while the concrete was hardening. So, and the like a hole would form around the fiber itself, and that changes the embedment length. So most of those fibers, a lot of them would just, you could just pull out of it. The bond strength wasn't as good as the fibers on the lateral plates.
Okay, I can see that there are two questions from the audience. Sofiane, would you please read them?
In fact, there is the first one from Jean-Michel Torrenti, and he said, could you explain your strategy for the approximation of the parameters? Because maybe there are several solutions.
There could be several solutions. We just did it trial and error style. We just repeated the test until we got the result that would be similar to that which we got from the experimental tests.
How you choose what is the good diagram, and you said, oh, this one, I will keep it to analyze?
Well, how I understand it is those that are, well, the group of them which are the most similar between themselves. Okay. The others who are too high or too low, we would just think that we did some kind of mistake and take it out.
Okay, another question from Stefan Grunewald. Do you intend to measure the fiber orientation of the polypropylene in element? If yes, what technique do you apply?
No, we didn't do this. We just see it as it would be very good to do this kind of thing. It would make the model more accurate, but at this point in time, the research we did was only with one fiber in the pull-out test. The orientation, it was just straight, placed straight in the cube.
Okay. Another one from Hamza Alam from Marseille, and he said, thank you for the presentation, and how do you think edging of the matrix would affect the bond between matrix and the fibers?
What does edging mean?
Edging is le vieillissement
time influence.
Durability, yeah. With time, the performance of your matrix will evolve, and how this evolution can affect the bonding between the matrix and the fiber.
When time goes on, the concrete hardens a bit more, so it should improve the bond mechanism between the fiber and the concrete. At least I think so.
Okay. For me, I have one advice. I think that avoid sometimes just reading the text, because even we are in Zoom meeting, when you read the text, it's a little bit boring, for example.
Yeah, I know, but it's hard to explain everything.
I know that it's hard, but try to make some effort to make it more direct and avoid reading text. And I have some question. In fact, how you choose the length of the fiber seeking in the concrete? You can have a fiber failure or debonding or the concrete failure.
It was determined. It was determined during the literature review that the most effective fiber length embedded in the concrete is about 20 millimeters. If the embedment length is bigger, the fiber would break. It also
okay. Just stop. Okay, I take this answer. But what are the parameters that affect the length of the fiber?
There are
to choose if there is debonding or.
As I've said, we just found in literature that was the most optimal length for this kind of fiber, synthetic. It's also depends on the type of concrete you use, of course. But we just change the concrete mixture so that the fiber would bond with it best.
Okay, but you know, if you change the diameter of your fiber, if you change the yield the yield strength of your fiber, you have to change the length.
Yes, I think, but these tests were done just for these types of fibers. We didn't really think of changing anything, the fiber type itself, I mean.
Okay, and then this is my last question about you said in some slides you put this is the successful attempt. Okay, but how you choose?
We chose the successful attempt was the attempt that was most similar in the
slide
in the energy, the graph.
Slide 17, yes. In slide 17 you have some
these.
Yes.
So how I understand it is that we just chose the one who has the most similar area beneath the graph. If the area, the average area of all the graphs of the experimental tests would be the most similar to the area of the numerical test.
Okay. Okay, but for example, in this diagram that you show, for me, the first one at the left.
Unsuccessful attempts.
Successful? No?
Well, as I've said, here you would get a completely different area under the graph. So that's how we determined that it's unsuccessful. That's the only parameter we looked at.
And also I have a question, because in the y-axis we saw that you have around at the maximum 200 Newton, which is something really high.
No, it's one fiber. It's
okay. It's a 200. It's like this. It's not a question. It's 200. But your the transducer that you use and also the equipment that you use, is it sensitive?
Yes. We looked that it would be sensitive enough to measure this.
Enough, because it's very low.
It's very low. We understand it.
In all our labs, we have a machine for 10 kilonewton. Then to measure 200 Newton is really challenging sometimes.
We use the apparatuses to measure these things just for these kind of small.
At your apparatus, it seems to me that the apparatus is something more adapted for a higher level of strength.
It is, but I think it's only 5 kilonewtons.
5 kilonewtons. Okay. Okay. Is there other questions? No, I think we did everything. Then maybe Balas, you can finish the presentation.
Thank you very much.